Okay, so we will start with density plots. Okay, density plots. Till now, we have seen about histograms, we have seen about bar plots, we have seen about box plots, right? So this is about density plot. I mean, density plot means it has to do something with a probability density. Okay, so you can know the probability can lie between 0 and 1, right? So same concepts will be applying here, right? So you will see that in a histogram, you can check the density out. So density plot is nothing but a smoothed version of a histogram, right? In histogram, you have like bins. You have bins. So what you can do is like you can draw a curve which can lie on the peaks of the histogram. Okay, that's like a density. Okay, so we'll see how it looks. So density plot is another way to visualize your univariate distribution, right? So you can see it is known as sometimes KDE plot also. Density plots are also known as KDE plot often, right? So KDE means kernel density estimation. So you can see they are usually created. This line is a bit technical. This line is a bit technical, like it is usually created by drawing a normal distribution centered around each data point in the bins, in each bin, okay? And then smoothing it out, okay? You will smooth it out, okay? You will not only join by lines. I mean, this is not, in each bin, if you do this, then you will have something like this, right? It is not smooth. Is it smooth? No, it is not smooth. Why? Because it has a kink. It has a kink here. Whereas this is smooth. This is smooth, right? This is smooth. So there is a difference between them, right? So you can see this you are just joining by the straight lines. But this you are trying to fit like maybe through a polynomial fitting or like a non-linear fitting you are doing it there with the set of data points, right? And in the density plot, whenever you see, so you will see a curve in the density plot, okay? And that curve will be such that the area will be normalized to 1, okay, because of probability concepts involved, okay? The area will be under the curve will be 1, okay? So you can see in one line you can say the KDE plot is nothing but a smoothed version of a histogram, right? We will look into a plot and we will see why it means like that. Okay, so I will show you here. So you can see this is the don't just see this and this curve for now. Okay, just see the two curves, that is histogram and then the curve below, right? You don't have to look into this plot right now. I will cover this plot later. So you can see this is a histogram in the background, and corresponding to that histogram, you are doing a kernel density plot or a density plot here. Okay. So you don't have to do anything. You have to give the data automatically. The command can find the density plot for you, right? So through Seaborn, we will be doing it. And so you see here, this is histogram. Okay. This is the density plot. This is the density plot, and this one, the below one you see here is nothing but also known as the rug plot. Okay, it's the rug plot. So it looks like the rug distributed, right? So we'll see what is this rug plot. It has its own advantages. I mean, the same data, we are showing you different versions of how you can visualize them, right? You will see that what this density means. Okay, we'll see what this density means. Anyway, so you can see, sorry, where we were? Here. Okay. So you can see that a histogram counts how many data points fall into bins. You can see the frequency on the y-axis, right? For a particular bill count, how many people have given that money to the restaurant, right? How many people? So that's the frequency. So that you count. But whereas a KDE, a density plot, estimates the probability density function of the data. Okay, it estimates the probability density function. You also know this as PDF, probability density function of the data. Basically, it answers if I pick a value of total bill at random. Okay, I want to know what fraction of people have spent in the restaurant around $30. Okay, around $30. So you can see how likely is it to appear. how likely people are spending $30 in my restaurant. That the density plot will give you the idea. Okay. So this is how you see the density plot over here. Okay. Uh, Maybe I can show you this also, like, yes. So I think fine. So you can see, like, to create density plots, like, we need two features or objects. One is den and another is x, right? What is den? Den is represents the whole canvas of the figure, right? It represents the whole figure of the whole canvas. Whereas x is, you can see, this is the axis object and it is the plotting area inside the figure. Okay, x is the plotting area inside the figure, whereas den is the whole figure or the whole canvas. Okay, fine. So you can see we are importing Seaborn as SNS. Okay, we are importing Seaborn as SNS that has been defined in previous code. So it's the subsidiary code below it. So we are doing SNS.kde plot. SNS.kde plot. That means you are telling that I need a density plot. KDE is the kernel density estimation, and I need a density plot, KDE plot, right? And you are saying what you need, data equals to tips. Okay, so you are telling that you take the tips data set, that's a predefined data set in Seaborn. So you take the tips data set and give me a density estimation of total bills. Okay, since it is univariate, since density plot is univariate, you need only one variable, right? So I hope you understand. So since density plot is a univariate plot, you need only one variable to pass. What is that variable being passed here? Total bill. Okay. So x equals to total bill and ax equals to ax. That's fine. So you can see a KDE plot is like a smooth curve of version of histogram we already saw. And instead of bars, just like histogram, it estimates the probability density of the variable, right? So it will estimate, in this case, it will estimate the probability density of the total bill. Okay. Fine. So you can see over here. So you can see persons, how likely that a person spends $10 or $20 or $15 in the restaurant is the maximum. So number of persons, the probability of a person spending $15 in a restaurant is high. Okay. The probability of a person spending $50 or $60 in a restaurant for food is very low. You can see it here, right? The probability on the y-axis is very low. Okay. More than $60, no one has spent. More than $60 in the restaurant for food, no one has spent according to this data, because more than 60, we don't have any data and almost the probability is going to zero, right? So you can see the probability density, what is the use of density plots, okay? If you want to analyze any of the variable, okay? So you can do a similar density plot for how many persons who are spending $30 or $20 are smokers, okay? Are smokers. What percentage of people are smokers who spend a lot of money? Or smokers, do they spend a lot of money or less money? Okay. So we think that smokers usually won't put a lot of money because they already have used their money in smoke. Okay. So that's the kind of logic. Okay. So you can see lot of analytics through this. So I hope that you can have some intuition about what this plot can do for you, right? You are getting, right? Or maybe you can see, like, maybe for bio AI, maybe you can see how many persons are getting affected or how many persons have genes of this variant, right? How many persons have this pattern of genes in them. So you can have a density plot over the population, right? So it can tell you that yes, the O blood group also, which blood group is more prominent in this class. You can do the histogram, you can also do a density plot, right? In that you can see whether the O blood group has the highest or B plus is highest in probability, right? Can, if we take any person in random, then high likely that that person can represent the highest probability in the class, right? Most likely. That's the idea. That's the idea. So this is the density plot, okay? And similarly, we can look into different plots. So these are some of the ideas written here for your sake. So okay. So this code we already discussed all this. Like it represents the probability density, and the peak of the curve shows the ranges of the total bill that occur most frequently, right? So which one occur most frequently? $15 occur more frequently, right? So a long tail to the right shows that if there are few occurrences of the larger bills occur very few number of times, right? So therefore the probability is very less. And why not just use a histogram? So the difference between the two plots is shown to you. A histogram is discrete, that means bin sizes, okay? The number of bin sizes, it is discrete, but we don't have gaps in histograms. Whereas density plot is a smooth version of the histogram, and it is very easy to compare any distributions, okay? It is very easy to compare any distributions. I mean, if you have two different variables, you can plot the density plot side by side, and you can check how the two distributions vary instead of just checking the two histograms, right? Then you have to worry about the bins, the bin labels, the bin range, and the height of the bin and all those things. Fine. Okay, so if you want to quickly see the shape of your data distribution, how your data is being distributed, then most likely you should use the KDE plot. Most likely you should use the KDE plot, right? Okay. So let us come back to another plot known as the rug plot. Okay. So as rug lies on the axis, so it will also lie on your x-axis. Okay. So how rug looks like? So in this plot, you can see, first let me show you the rug plot. What do I mean by that? So in this plot, you can see that a histogram is there. Okay. And corresponding to that histogram towards the bottom of your axis inside the figure, we have like lot of vertical lines. We have lot of vertical lines. I hope you can see these lines. Okay, I hope you can see these lines. Now, what does it mean? It means that whenever a bill is encountered, you put a vertical. I mean, see this guy, it is $6, maybe $3 something he is spending. Okay. And if someone is spending $3, yes, I put a vertical line. Whenever a particular person is spending some money, you put a vertical line according to that value, right? So then you see a distribution. Okay. So how many number of clicks will be there? The number of clicks will be the number of customers who are spending the amount, right? So can you see what is the advantage of this rug plot? If you do like that, if every customer goes and a vertical line is put, then what idea it gives you? Can you see that some vertical lines are very close to each other, whereas some other vertical lines are very bit spaced, a bit more spaced, right? So you can see the person's spending in between $10 to $20 is very clustered, right? They are very close to each other, right? That means the occurrence is very much. There are a lot of people who are spending a dollar bill around $10 or $20 in between, right? However, you can see as you go more than $30, the frequency has reduced. Okay, the frequency has reduced, and in between $47 or something, again there is a tiny cluster. Maybe 3-4 people are spending that money. Okay, but you can see huge chunk is here, huge chunk, and also in $20 to $30, but lesser than $10 to $20. The number of people spending amount from $10 to $20 is higher as compared to people spending $20 to $30. And same you can corroborate, like have a correspondence with the histogram, right? In the histogram also you can see in between $10 to $20 there are bigger peaks. There are bigger peaks. In between $20 to $30, the peaks are a bit smaller than the peaks in between $10 to $20, right? So you can visualize like this, okay? So usually what happens is in a single plot, in a single histogram plot, it is better to draw the density plot. It is better to draw the rug plot in the same figure so that you can see multiple observations through multiple diagrams or multiple plotting types, right? So therefore we have plotted both the histogram and the rug plot in this case. Now you can see for histogram, you know hist plot, right? So similarly for rug plot, you can use sns.rugplot. And which data set it is taking? It's Gibbs data set, and the univariate variable it has to consider is the total bit. Okay, x equals to total bit. That's the univariate, like the variable you want the distribution about. Okay, fine. Okay. So again, the same things here already told. You can just have a read. Okay. A rug plot draws a small vertical tick mark on the x-axis for each of your bill observation, right? Each tick means one restaurant bill. So it shows the raw data distribution along the axis with the number of vertical ticks, right? So if many ticks are close together, it means many bills are in that range, right? Of course. So therefore I told you that in between $10 to $20, there were a lot of vertical ticks close to each other. So what does it mean? It means that more bills are in that range, like more number of people have spent money in that range, right? So macro histogram, like you can see the macro version, like lot of bills are in the $10 to $20 region, right? Whereas rug gives you a bit of micro version to that. What it tells, oh, there were a lot of exact bills at $12 and $15, right? So in here you can exactly see what value, exact value has lot of occurrences. Okay, so you can see that both histogram and the density plot is kind of giving you and going hand in hand in giving you some insights about your any one variable. Okay, so these are some of the plots. Now, now we are seeing that if you get lot of different plots, if you get lot of different plots in the same plotting section, it will be beneficial to you, right? Like you saw that we plotted histogram and rug plot side by side, right, on the same plot. So instead of typing this two line of code to do this, is there a single line of code which can plot all different kinds of plot automatically in our code, right? So therefore that motivation gives us something like distribution plots. So this motivates us to come to distribution plots. Okay, what is distribution plots? So you can see in a distribution plot, you can have these three in together, right? You can see that I can have a histogram, I can have a density plot, and I can also have the rug plot in the picture. Okay. Now, okay. So before doing that, maybe you need some more concepts. So we'll come back. I think these are fine. Okay. So this is the distribution plots. Okay. So this is a newer version. There were two versions. One version was the DNS. Dist plot. This was the older version. SNS.dist plot. Okay, that is a distribution plot. But there is a newer version that is SNS.distplot. So try to see the difference between them. There is a difference of T in between the two. Okay. So that is a newer version. Okay, that is a newer version. So the newer distplot function allows us to put together many of the univariate plots together. Okay. So if you want lot of different univariate plots together, you can use sns.distplot. Okay. So it is a successor to the older distplot function. Okay, with different new features and all. But as usual in many of your histogram plot or your line plots or like bar charts or box plots, the output you are getting is an axis object. Okay, like on an axis object, different features are plotted, right? Whereas in a dist plot, since it is doing lot of different types of univariate plots together, you won't get an axis object. Rather, you will get some other object known as facet grid object. Okay, so these are known as facets. Okay, what are facets? We'll come to that in different slide. So you can see the sns.distplot function returns a facet grid object. Okay, and not an axis, not an axis. So the way we were doing the box plot or we were doing the histogram, the comments in this will be a bit different. Okay, and I think it is worth it. It is worth it because within a single line, you are able to get lot of univariate plots together, right? So you can see, so the way we have been creating a figure and plotting the axis does not apply to this particular function here. So when you will see the disk plot, it might be something new to you. Okay, the comments you are writing there, it will be something new, and it won't be similar to the histogram or the density plot or the rug plot you were doing. Okay, the subtle difference between this is the previous univariate plots were giving you an axis object in output, whereas the disk plot function will be giving you a facet grid object. Okay, that is different from the axis object. So of course this is complex. Of course this is complex. So but what is the benefit? So the benefit of returning a more complex object, that is a facet grid object, is that it can plot multiple things at the same time. At the cost of that, we are, considering the facet grid object. Okay, fine. So before that, let us come to what are facets. Okay, what are facets? So you can see a facet is just like a subplot. Okay, and it is automatically created based on the diskplot function based on a categorical variable. Okay, so basically it is a subplot. So it is not much new to you, but it is just like a subplot. But it can handle lot of different univariate plots together. That's the advantage of these facets. So instead of manually, so try to see this. Instead of manually, I mean, if you want multiple plots in a single, or in your figure display or your canvas, you have to write 3-4 lines of code, right? One for histogram, one for rug plot, one for KDE, okay, one for some other distributions, right? But you don't have to do that. If you just write disk plot, it will automatically find which are the categorical variables in your dataset. It will automatically compare different variables with each other and make the plot. That's the idea of a facet, right? So it will, instead of manually splitting your dataset and creating multiple subplots, Seaborn can do this for you. Okay, so it saves you from manual doing those things, manually typing many things, right? So you can see each subplot shows the same type of plot, but they will be filtered based on specific categories, right? It will automatically find which are the categorical variables, and it will, like, suppose X, Y, Z are there. Okay, so it will make one for X, one for Y, one for Z automatically. You don't have to do it manually, one for X, one for Y, one for Z. Okay, that is the benefit of using this. So basically, you will get lot of subplots. So that is like a grid of plots. So that will be like a grid of plots. That means you will see something like this. So this is like a grid, right? So you can see this is like a grid, right? So it's a 3x3 grid, 3 rows, 3 columns, and in each grid you have a plot. Okay, and how that plot is coming through? That plot is coming through different categorical variables. Automatically, it checks and compares the categorical variables for you and makes the plot. You don't have to give it manually, right? Okay. So therefore you can see what the each row and column means to your category of your data. Okay, so maybe this is category 1, this is category 2, and so on. Different categories you have in your data sets. That many times it will make your plots for that. Okay. So that's the idea. So yeah. So idea of facet is to split your data into groups and draw one subplot for each of the groups. Okay, one subplot for each of the groups. So okay, fine, that's okay. So these are some of the examples. Like maybe you have time column in your data set. It can have lunch or dinner. So how many people have taken lunch or how many people have taken dinner? That is a categorical variable. It can automatically do a univariate plot based on that. Okay, fine. I mean, okay. So So same things only. So why we will use facets? If you want to compare patterns across different categories, right? Then you like to create facet objects. So something like male versus female and smoker versus non-smoker, right? Maybe what you want is something interesting. You might want a relationship between how many males are smokers, how many females are smokers also. So therefore, this kind of permutation combination is being taken care here automatically. You don't have to do manual. So you have multiple relationships and these are separated by categories, okay? Different categories. Of course, it will keep your code clean without manually creating these subplots. Okay, that's the advantage of this guy here. I think this is it. Yeah, this is it. So let us see the plot here now. Okay. So you can see over here, like how I have created one disk plot here. Okay, how I have created one disk plot. You can see fig equals to sns dot disk plot and data equals to tips. Let's take the tips data set and x equals to total bill. Okay, and kd equal to true, rug equal to true. That means I want density plot in my disk plot when you are displaying. I also want rug plot in my display as well. Okay, you are telling that. If I suggest you can type false here, then the plot won't occur in your final output. If suppose you put rug equal to false, then you won't see this plot here again. Okay, so when I give you this collab file, these things you should try. Okay, try some other plot, comma some other plot equal to true also. Okay, and see that whether it is giving you a new plot. Try to keep some things as false which are already marked as true, and then see the changes in your plots, what changes it brings. So these are some of the things you can play around with your collab file when I share it with you. Okay, so you can see like here we have only one facet grid object with different plots. You can see that with this facet grid from this plot, Seaborn can automatically split your data by a categorical variable, create multiple subplots at once, and can also add hue, row and column parameters. Hue means depends on the size. I hope you remember a plot where we did multivariate distribution, where we gave the bubble chart, right? Where we had different size of the bubbles. Okay, we had different bubbles sizes for different another variable, like a third variable. Maybe the male is one color, female was given another color. Maybe and also like one value was assigned to the size of the bubble, right? We did that. So indirectly, that plot was kind of assessing 4 different variables in the 2D plot. So that's how you can handle this multivariate plot. But I want to show you, I mean, different figures, but I'm not having it here. Let me show you that. Did I have here or no? Okay, let us see that later. Okay, fine. Scatter plot, I will not come to it again. Scatter plot you already know. Let us see that in a scatter plot. In a scatter plot, you have this. Suppose you have this scatter plot here, like lot of different points scattered around, but it is not giving you much of the visualization to your data. I mean, you need some regression line to it. Suppose you need a regression fit to the scattered plot, right? So if you want to do that, how can you do it? Okay, how can you do a regression line in your scatter plot together? Okay, so that brings us to something known as reg plot. So you can see you can also create a scatter plot and also draw regression lines simultaneously. Okay, if you want a scatter plot and also want to draw a regression line simultaneously, then reg plot is the plot you can go with. Okay, so the same I mean syntax, there is no different syntax, but this is bivariate. I please make sure this is not univariate, right? This is bivariate, because whenever you want to compare two different variables, it's a good idea to use scatter plot or line plots, right? Because you are comparing how one variable changes with respect to the another variable. Okay. If you have a single variable, then histogram, bar charts, and all those things are the best to go. Pie charts, these are the best to go. But if you want to compare two different variables, that is means it is bivariate, it is better to go with scatter plots, line plots, right? So anyway, so you can see SNS.reg plot. Reg stands for regression, right? You can see X is the total bill. So total bill will be on the X-axis. Y equals to tip. So that's on the Y-axis, right? And you are creating, it will automatically create the regression line for you. Okay. So you can see that you can see the plots, the individual line that is scattered and also fits a linear regression line through that. It also will fit you a linear regression line through the to your scatter data points, right? Now I want to give you a bit of a thought which I have not covered here. What is the thought is like if you have this regression line, then what are the you call like the background behind the regression line? Do you see any background in the regression line? So what is that? That I want to ask. Okay. So next class someone should tell me. Okay. So why you see this buffer kind of thing behind this top and below the regression line, and what does it stand for? Huh? Then there should be some technical term for it. I mean, it can go maximum to that, minimum till that, fine. But does it remind of anything to you? Okay. So this I suggest that please try to find yourself and let me know next class. Okay. Let me know next class. This I have not told. Okay. Now let us come to a very nice plot. Okay. Which normally we don't do. But it is good in looking. Okay, the plot looks good if you do that. Okay, that is something known as a joint plot. Okay, that is something known as a joint plot. The joint plot means you will see you bivariate distribution scatter plot as well as some univariate plots as well. Okay, and the way it places on different axes is quite interesting. Okay, so you can see we can also create a scatter plot that includes a univariate plot on each axis using SNS.jointplot. So on each axis you will have a univariate plot, but in the main figure you will have a bivariate scatter distribution, right? So one major difference is the joint plot doesn't return axis. So we do not need to create a figure with axis on which to place our plot. That's fine. No need to worry about this. So same thing, SNS.jointplot. You give the two variables here, total bill and tip. It will automatically create a univariate distribution for total bill. It will automatically create a histogram for the tip also. Okay, so I will show you the plot again here. Can you see? So x-axis is the total bill, y-axis is the tip, right? It created a scatter plot for this, fine. Now the joint plot will also do one more extra thing. What is that extra thing? It will also do a histogram of the univariate variable that is total bill. So here you are seeing the total bill histogram, okay, on this axis. Whereas you will also see the tip distribution of histogram here on the y also. This automatically the joint plot will do for you. Okay. If you have x versus y, it will do a scatter plot for you. Fine. And in addition to that, on each of the axes, it will place a histogram based on the x histogram and y histogram also. Okay. That is the joint plot. Okay. That is the joint plot. So we will go through many different plots in this class. Like, I mean, the aim of this class is to give you different ideas of how we can visualize things and what kind of different weird plots we can generate. Okay, you will see a lot of different things. Okay, as we go through something known as hex bin plot. Okay, so people thought that if we just draw a point, it is not that efficient. I mean, a scatter plot is not that efficient. So what they thought is, instead of just a tiny bit of a point, why not we draw a hexagon? why not we draw a hexagon around each point? Okay, so therefore each point you can see it's a hexagon. Okay, each point you can see is a hexagon. So therefore, due to that, we have got this name as hexbin. Okay, hexagon. Okay, fine. Okay, so you can read this. I have written down for you. So scatter plots are great for comparing two variables. Already know about it. However, sometimes there are too many points for a scatter plot to be meaningful. Okay, there are so many points for a scatter plot to be meaningful. One way to get around this issue is to bin and aggregate nearby points on the plot together. Okay, so that's how histogram does. I mean, histogram can bin the values for you, and you can get a frequency of which value occurs how many times. Okay, fine. But it is also interesting to create a bar with like hexbin plots which can bin two variables at once. Okay, so instead of just random points like circular points or dots, you use a hexagon for this purpose, right? Because it is believed to be the most efficient shape to cover an arbitrary 2D surface. Okay, if you have a 2D surface, then a hexagon is believed to cover it more efficiently. Okay, I hope you might have learned about this in solid state in your class 12th about BCC and FCC lattice. Okay, so the packing fraction, the packing ratio, and all those things you are trying to compute. And you found that whenever you are comparing it with the hexagon, it is giving you the highest packing efficiency. So how to do this? How to do this? So you can see over here, it is just like the joint plot, but there is one catch here. The kind of plot you need is equal to hex. The kind is equal to hex. The kind is equal to hex. Okay. So if you use the kind is equal to hex, it will create a hex bin plot. Okay, it will create a hex bin plot for you. So the darker, so you can see there is a hue. There is a hue like that means like, so someone ate it. Okay. Okay, so let us start like, so you just need to put your kind here. You just need to put your kind here, and the kind is equal to hex. Kind is equal to hex. Okay, so kind equals to hex means it will create a hex bin plot. But most importantly, this is working very nice. So the idea is like in hex bin plot, you see hexagons. So the idea is some hexagons are darker, whereas some hexagons are a bit more transparent. So therefore, that is a kind of a variable. Now, what does it mean? What does it mean to be darker, and what does it mean to be in transparent version? So you can see the darker hexagon means more points in that area or higher density. So you can see the hex bin plot. You can see these guys here, which are very dark in color. It tells that lot of points are concentrated around that region, whereas lot of points, very less points are concentrated in this region or this region here. So if we go to the scatter plot, we can observe the same thing, right? You can see lot of points are have higher density in this area. Remember that you are dealing, let me be very clear with you, that why hexbin is actually needed. I mean, you are having a bivariate plot. That means two variables. If two variables come to picture, you are no longer playing on an interval on one axis. Rather, you are playing on two intervals. That means you will be scanning the area. You will be deciding the area now. Okay. So now the idea, so therefore people thought about hexbin plot. So hexbin plot only comes when you have a bivariate distribution, when there are two variables. Okay, doesn't make sense. Hexbin plot doesn't make sense if you have univariate. If you have a univariate plot, hexbin plot doesn't make sense, because hexbin plot you only create when you have two variables, x and y. Okay, so therefore you can see from this plot, it is a bit difficult to analyze. I mean, if you have lot of points, it is a bit difficult to analyze that around this area you have a higher density of plots as compared to this area, suppose, right? So therefore, when you create hexagons, we believe it won't be missing out any area, okay, because hexagon is believed to cover the most of the area efficiently, and that hexagon, if it contains lot of points, will be colored very dark, right? So if the hexagon here will be colored dark, it means that it will have a higher density of points there. But hexagons here in this my mouse cursor will be plotted in a very transparent way. Why? Because very less points are there, right? And hexagons here also will be colored a bit more less dark as compared to hexagons here. Is that the case? Let us see. Yes, you can see that, right? So you can see hexagons here are very dark, right? What does it mean? It means that in this area, in this area, you will have a lot of density of points as compared to other hexagons where the color are bit less transparent, right? I hope you are getting the intuition. You are getting the intuition, right? Okay. Now the idea is like similarly, you have created a density plot for a univariate variable, right? You created for one variable a density plot. Exactly. Now the idea is if you have a bivariate distribution, like a by two variables you are analyzing, how can you create a density plot? So that motivates us to come to 2D density plots, like bivariate, 2D density plots. So you can also create a 2D kernel density plot. This kind of process is same as SNS.KDE plot as you did for your univariate plot, right? Except that it creates a density plot across two variables or bivariate, right? We will just see the plot just to have an idea. So you can see here, right? If you have total bill and tip as two variables, how your density plot is looking like. Now, what does this show? That is more important, okay? Fine, you can also create, what happened? You can also create something like this. I mean, no coloring inside. It is creating just contours. These are contours. Each curve is a contour. Okay. So you're creating contours. This is a 2D density view. Okay. However, you can plot separately for each variable a density plot. For each variable, you can create a density plot. How? You on x-axis you can see this is the density plot. On y-axis it is the density plot. It is just like the joint plot, right? It's just like the joint plot. Let us see. Okay. Fine. So the same thing. So you can see SNS.KDE plot, but instead of passing, previously remember that you were passing only x. Previously you were passing only x is equal to total bill. Now you are passing a y variable also, that is tip, which tells it that it is a bivariate distribution. Okay. Previously you had only x. Previously you had only x equal to total bill. Therefore you are getting a density plot, like line plot like that, right? Now you have two variables, x and y. So that returns a 2D contour to you. Okay. On x and y variable, it returns 2D contour. Okay. You can see contours or colored regions. They represent where the points are densely clustered, right? Oh, here also same as your hexbin plot. The idea is the same. The darker the areas, the higher density of points are seen. Okay. So you can see again the same idea. In this region, it is darker. That means lot of points are falling in that region, right? And this area is becoming very less transparent, like more transparent, sorry. Then it is having less density of points, right? So the idea is like if you have 2D density plot, you will be getting contours. And this is another thing which I want you to experiment, that do you want shade or you don't want shade? This plot is with shade. Okay, this plot below is, you can see, is with shade. So shade is equal to true, right? I suggest you keep shade equal to false. If you keep shade equal to false, then what you are getting? That's my question to you. Okay, the shade won't be there. I mean, shade equal to false means shade won't be there. So what you will be getting? That's my question. So you can see the plot below is again showing you a joint plot. It is again showing you a joint plot of KDE, right? So indirectly what it will do, it will plot the density plot for each of the variables involved. on the each axis, right? So here you can see it has plotted on the x-axis its corresponding density plot of total bill. On this side, it has plotted the KDE univariate density plot of tip. Okay, I hope that is fine. Okay, I hope you're getting the ideas. I mean, how we are giving different sort of visualization techniques to visualize different kind of the same variable, different plots for same variable, right? Bar plots, I will not go through. It's done. Did we cover box plot also last class? That's fine. You know about this outlier, this. Okay. Now let us come to something like a violin plot. Okay, this is another sort of plot, violin plot, because it looks like a violin. Okay, therefore the name is violin. Okay, so but the violin plot, for a violin plot to be made, the box plots have a greater weightage. Okay, so inside the violin plots, you will be seeing box plots. Okay, inside the violin plots, you will be seeing box plots. Okay, so the violin plots, you can see the box plot are a classical statistical visualization, but it might be a bit difficult to understand the distribution of the data. Okay. Now, if you want to understand the distribution of the data and you want something different as compared to the box plot, then we come to the violin plots. Okay. So violin plots can show the same values as a box plot, but it plots the boxes as a kernel density and estimation like KDE. Okay. I mean, you can see how it looks like. Okay. Can you see what is happening here? You can see that there is a box plot inside each of the variable. Okay, inside each of the variable, each of the categorical variable, there is a box plot. For lunch, there is a box plot. You can see what is this white line. Okay, and you can see what is this whiskers here in the box plot. And what are these? I want to ask. What are the boundaries? Okay, what are the boundaries? Okay, so these are some of the questions and why it has been shaded. Okay, can you have a control of the shade? That's my question. Okay, fine. So we will begin with some other plots. Okay, so we will start with violin plots. Okay, why violin plots are needed and how they represent and need help from box plots. Okay, that's the idea. Okay, so you can see from the figure. Okay, you have the box plot for each categorical variable. For lunch variable, you have a box plot. And so what does it mean? For lunch variable, how much total bill is obtained? How many people has come during lunch and had lunch and how many people ordered at what amount? Okay, that is the box plot for that, right? It's a univariate. So you had a box plot. Similarly, for dinner, you have another box plot, right? Now the effect is what you see behind these boundaries, okay? The more the width of these boundaries, the more density it has. Okay, that means the more occurrence it has. So you can see for lunch, the spending between $10 to $20 on the y-axis has a larger density as compared to other values of the total bill. Okay, so you can see that. Okay, open. Okay, so I hope that is clear. Let us see. So for violin plot, you have to just do sns.violin plot. sns.violin plot. And you have to specify two values here, right? You can see the time, that means the lunch or the dinner. That's the time variable here. X equals to time means on the x-axis, you will have two categorical variables. That is either it is lunch time or dinner time. And y-axis, it has total bill. Y-axis, on y-axis, it has the total bill, right? And your violin plot will automatically consider those two variables and perform the plot, the violin plot. Now you can see the width of this violin plot. the width, there is a width of this violin plot. This has the largest width and then it gets smaller and smaller, right? So you can see that the width of this violin at each y value, that means you can consider these sections, okay, these sections. So at each y value, it represents the distance, the density, okay, it shows how common the value is, how common the spend is, right? So from this, what can we understand? From this, we can understand that during the lunchtime of the day, people spending $10 to $20 are more often. Like people often spend a higher occurrence of $10 to $20 during lunchtime. However, during dinner time also it's almost the same statistics. However, it is a bit more on a higher note, right? You can see the width has gone a bit higher. I mean, higher spending in dinner than compared to the lunch. Okay. And what's the white dot you are seeing in between the box plot? That's the median. Okay, that's the median of the box plot, right? This is a white bar you are seeing here. So this is all about the, you can see, yes, the white dot is usually the median. The thick line shows the interquartile range. So this thick line you are seeing is nothing but the interquartile range, right? So that's what we learned about the box plot so far. So this is what is known as the violin plot. Now, the idea is, can we color the violin plot a bit differently? Yes, you can. But before that, yes, this is how we will compare. Let us compare the violin plot with the box plot, okay? So to see how violin plot is related to the box plot, we will create a single figure with two axes, AX, ES. What does it mean? Two axes means two subplots. That's what we saw the difference last class between AX, IS and AX, ES, right? So you can see SNS.boxplot, SNS.violinplot. Okay. So we will see two subplots. One, the first the box plot, second is the violin plot, right? So you can see the difference between them, right? So this is just for you to see. Like you can see the width of this also, like the box plot. The same region you are seeing the width here also, right? So, and the maximum value here is also corresponding to the maximum value here. So you can see the correspondence between the two plots. Even see the maximum value here, that kind of matches the maximum value here, right? So you can see the correspondence between two plots, right? However, if you want density to be involved, it is better to prefer the violin plot as compared to the box plot, because box plot doesn't give you any idea of the density, whereas the violin plot gives you an idea of the density. This is the density. The wider the violin plot is, the higher the density at that point it is, right? So width of the violin plot corresponds to the density of its occurrence. Okay, how frequently that value will occur, right? Now there is something known as a pairwise relationship, which is quite interesting and useful. Okay. So when you have mostly the numeric data, I mean, if you have only the numeric data, when you only have numeric data, then visualizing all of the pairwise relationship is quite interesting and important as well. For that, you have to do pair plot. Okay, pair plot. What is the benefit of that? What is the benefit of pair plot? You will see this. Instead of manually creating the multiple subplots, which will take 20-30 lines of codes, with just one line you can write here. Okay. So you just do sns.pairplot data equal to tips. No variable is being mentioned. No variable is being mentioned, but make sure that your values are numerics, okay, in your data set. Then it will automatically find, okay, then it will automatically find which are the numeric variables and will compare with each of them. Like here you can see, here there are three numeric variables, that is total bill, tip, and size, right? So anyone can have a question that how total bill is varying with respect to tip, with respect to size, right? How tip varies with total bill. So all kind of permutations it can do. But one thing you should look in a pairwise plot is the diagonal is all about this bar plot and histogram. The diagonals, you can see, think of this as a matrix. Think of this grid object as matrix. Then the diagonal, that is 1, 1, 2, 2, 3, 3. These are nothing but constituting of the histogram and the bar plots. do you see anywhere histograms? No. That's how it is designed. That's how it is designed. So always in the diagonal, you will be seeing the histograms or the bar plots, right? And all other cases, you will be seeing this scatter kind of plots. Okay. So you can see here how total bill, how total bill, yeah, how total bill is varying with respect to the tip. This plot corresponds to how total bill varies with respect to tip. How total bill varies with respect to the size. There is a size column in your tips dataset. That's how we made the size of the bubbles in your bubble chart. If you remember, the sizes of the bubbles were based on the size column in your tips dataset. So size is there inside your tips dataset. Okay, size is there inside your tips dataset. However, I don't know what the size means in the dataset. I mean the significance of that size, but it's a numeric variable. It's a numeric variable. So you can see, so through this multiple relationships, you can see within a single plot. Okay. So therefore, if you are bored, I mean, if you are bored to do a histogram, or if you are bored to do a box plot or a violin plot by typing, so what I suggest is you try pair plot. If you do pair plot for your data set, it will give you all kind of histogram and scattered distribution, right? So in a single plot. So this is something very powerful, I believe. Why? Because with just a single line command, you can generate this many set of plots. Okay. So if you just pass pair plot and the input to that is the data set, then it will create all kind of possible scatter plots and histograms. Okay. So that's how it is interesting. That's how it is more interesting. Okay. So this is about pair plots. So similarly, you can color the violin plots according to category also. Okay. Depending on the category, you can create the, distinguish the violin plots. How? Suppose you see here, I want lunch and dinner. I hope you remember the violin plot from the previous output, right? You had lunch and dinner, but you don't know how many are male in lunch, how many are female in lunch, right? So in order to do that, the same data set can be partitioned, right? So you can see that, and also, no, I'm sorry, like here it is not male, female, here it is a smoker, right? So that's another categorical variable. So same thing you can do with male and female also, okay? So smoker, whether the people who are coming for lunch, if it is blue color, they are smokers. If they are green color, they are non-smokers, right? So you can see for smoker, they have a box plot. For non-smoker also, they have another box plot. So based on the color, they are partitioned into two. Okay. So same you can see for dinner also. The left side is corresponding to the smoker, one box plot. The right side is also corresponding to the non-smoker, another box plot. Okay. So you can do this. So how we are doing this? So to do that, you pass a hue command. Okay, hue, H-U-E. That is, you say the categorical variable, like set the color based on a particular categorical variable. If you want to do some idea like this, like you set a color in the plot based on a categorical variable, that is whether if it is blue, mark as smoker, if it is green, mark as non-smoker. So we are coloring based on a categorical variable. If you do that, then it is a good command, is a hue command. So it will automatically create a color for you. So you can see hue is equal to smoker. That's the categorical variable. It will automatically set the color based on the whether it is smoking or non-smoking, right? When so we are splitting here. We are splitting the data set here. Split equal to true. I suggest you guys to try equal to false also. Okay. I suggest everyone to try with split equal to false also when I share the collab. Okay. So you see what's the difference you get when you try split equal to false. Okay. Okay. So this is this palette we are using, Viridis. And this Viridis palette is widely known that it can be used for colorblind people. So those who are colorblind can use this palette. It won't affect them. I mean, they might see 2, 3 colors as the same color, right? So palette equal to Viridis is one particular palette which can help colorblind people also. So that's how you can. So it's suggested that you try Viridis, because if they are colorblind in your like surroundings, they can easily check your data. Anyway, so anyway, like hue you are seeing, it divides each violin by a smoker status, like whether they are smoking or not, and each is being given a color associated to it, right? So you can see when you put split equal to true, what it does, it draws both categories inside the same violin. Okay, it draws both categories in the same violin, one on the left, one on the right. I would be excited for you to try and see what you are getting if you put split equal to false. Okay, then naturally it won't draw the two categories inside the same violin if you put split equal to false, right? So how then the plot will look? So that I share with you, like that's you have to share and maybe post on the group, those who can do. Okay. Okay. So you can see the hue, let us see something known as LM plot. This is known as the linear model plot. Okay. But here we have a passed hue command, like again with dots. Okay. Hue to smoker, hue equals to smoker. That means it will color for smoker, yes, equals to one color, non-smoker, another color. Okay. So that's the idea. Okay. And I have drawn fit reg equal to false. I mean, there is no regression line you are seeing. If you want a regression line, you can try true. Okay. So LM plot is a linear model plot. Here we have disabled regression with fit reg equal to false. However, I suggest you again to try true. Okay. So there are some chunks I want you to try, fiddle the code here and there. Okay. And see how it changes the plots. Okay. So you try the true here. Okay. Try true. So when you try true, I believe that you will get a regression line. How it is different from the scatter plot? Because you get a hue command here, right? You get a hue command. That means you can pass a hue command. If it is blue, it is a smoker. If it is green, it is non-smoker. So you can easily see that, you can easily see that the guy who spent less and gave a higher tip also is a smoker, right? Fine. Okay. So same thing you can do like pairwise plot. So it makes the plot even more visually attractive. I mean, the pair plot can make attractive visualizations. So one good thing about visualization is the more attractive you can make, more meaningful you can make, it is nice, right? So you can see the same pairwise plot we have drawn in such a nice looking diagram. Okay, only based on colors. So I suggest you try to use colors in your plots to make it more beautiful, right? And attractive also. So you can see like what we have drawn here, we have given the time as a hue parameter. Okay. I mean, it will be now colored. The points will be now colored based on the time, whether it is lunch, one color, dinner, another color, right? So let us see which color. Yes, you can see blue one is the lunch and the green one is the dinner, right? So you can see that this guy over here is greenish. That means he has come for dinner. Okay, he has come for dinner, right? I hope you are getting some ideas, right? And yes, same idea, like here instead of the histogram in the diagonal, you are getting density plots. You are now getting density plots, right? Fine. So these are some of the ideas, like yes, hue is the time, points are colored by the time category. Diagonal shows histogram or KDE plots of each variable. Here KDE, density plots. Okay. Previously you were seeing histograms or bar plots. Okay. I mean, yeah. If you want to make the entire figure smaller or bigger, you have another parameter for that, height. Okay. Yeah. I mean, if you want to make bigger each of the subplots, you have control of height. Okay. You can make each of the subplot bigger or smaller. You can make the difference with height. You can make height equal to 4 or 8 or something like that, and you can get bigger plots as well. Right? I mean, these you can, practice a bit. So this sets a ground tool for you. When I share this collab file, you can pass different values here. Height equal to 8, height equal to 10. See the changes in the plot. Okay, whether the plot is getting bigger or whether it is going out of bounds, what is happening, right? Try different colors, maybe try different palette here. Don't believe that only Viridis exist. There are a lot of different palettes on Seaborn, right? Lot of different palettes on Seaborn. You can color. Can you make different palettes and share different colors and see which color makes the plot even more attractive? Okay, but this kind of plot is even good, mostly for colorblind. Okay, but I suggest that you try to Google and know more about palettes. Okay, what are the possible palettes available in your Seaborn library, right? What are different palettes available? What happens if you don't do time, rather do smoker? If you put hue equal to smoker, then what happens? It will color based on the smoker. Smoker one color, non-smoker another color. Then how the plot varies, right? So these kind of things, I mean, you should be doing when I share the collab file. Okay, if you don't do that, you won't get a motivation of how, which parameter is important, what is the use of this here. Okay, can we make it false? What happens there? Which plot we want? So later when you want to do anything sort of like that in your projects, then you can check those palettes. Okay, which palette would be good for you, whether you want a divider or not. If you don't want a divider, then make it false. If you make it false, what's the advantage? What's the disadvantage? So there are a lot of aspects. So you can work with size and shapes. Okay. So you can see here we color according to the time, lunch and dinner. Okay, hue is time and size equal to size. So you can see as previously the bubble plot, it is similar to bubble plot. Okay. So you can see some plots are bigger in size, some plots are smaller in size. So how we decided the size? We put size equal to double quotation size. This double quotation size is taking the data from the tips data set. Okay. And the size of each point is being considered according to the tips data set. Okay. According to the tips data set. Okay. So therefore you are seeing automatically it is plotting some points as small, some points as big. And how they are colored? They are colored according to the time. That's the hue parameter. Hue equal to time. Hue equals to double quotation time. That means lunch blue, dinner green, right? So you see how it's a multivariate plot. It's a multivariate plot because 2 axes you are already considering, but you are considering another size, that is another variable in your data set. You are also considering another categorical variable, that is time of the day, whether it is lunch or dinner. So you are indirectly working with 4 variables here. You are indirectly working with 4 variables. So you can see even though it is a 2-dimensional figure, but you are sort of working with 4 different variables here. Okay. So that's how it is that's how you can analyze this multivariate plots. Okay. But size is not recommended. Doing size plotting is not recommended. It is believed that humans don't perceive the size properly. Okay. Anyway. So fine. Facets I already told you about. Facets I told you. Let us go to one interesting plot that I hope, how many of you are doing trading? Stock trading, stock markets, apps, Grow app. Yeah, good. Yes. Anyone here? No. Okay. So, in your stock markets, you normally see when you open the app and you try to see the stock of a particular company, you see a kind of a plot. Okay. And that plot is something known as a candlestick plot, right? So candlestick plot. So how you do this candlestick plot? You don't need to worry about the code, but this is how gone. Okay. That's the interactive plot. So that's the interactive plot. So what this does? So a candlestick plot is a standard visualization technique in finance, right? Used to show how a stock market price moves over time. Okay. So each vertical candle you will see summarizes one time unit. Okay. So with 4 variables, that is opening time and closing time. What is the opening price and what is the closing price, right? So opening price means the price at the beginning of the time period. Closing time means the price at the end of the time period, right? High and low, maximum price in that period. Low means the minimum price. Okay. So how you differentiate between red and green? if close is greater than open, then the candle is usually green and the price has went up. So it is a good thing for you, those who have that stock. Okay. If the close is less than open, the candle is red, so price went down. So it is a good opportunity for you to purchase that stock. Okay. So the rectangle body you are seeing shows the range between opening and closing. Okay. Anyway, so how this looks? So we are using Plotly for that. Okay, Plotly. Okay. So don't worry about this coding part, but check. This is not the real data set. This is not the real data set. Okay. So you can see how it looks like. Okay. So the x-axis is time. You can see January, February, March. Some are green, some are red. Greens are the good prices for to purchase the stock, right? Red are good things for you to try to sell it. Okay. So you can see the when you hover over each of the graph, you can see the details about it. So you can see, let me put my cursor over here. Yes, you can see that candlestick. Okay, it's looking like a candlestick. You can see the date February 5th, 2024. The opening price is 147 rupees or dollars, I don't know. High is 147, right? Since you can see that the high, the close is more than the open, therefore it is colored red. The closing price is more than the opening price, so it is marked as red, right? Fine. And the bars, the top bar and the bottom bar, you can see the highest and the lowest price. Okay, the highest and the lowest price. So each candlestick is giving you four values in total, like whether it is green or red, and it also gives you information about the opening price and the closing price, and also gives you information about the maximum and the lowest price, right? So this is how you do it for each of the time period, and you get this distribution known as a candlestick. Okay, candlestick plot. So usually more important in finance. So those who are doing stock market, or you don't do stock market, try to see your friends who are doing, and they can show you some plots. Okay, they are already experts in it. Okay, so good. Okay, so okay. Mm, okay, so so far we have seen, like, this is 1 minute. Yeah.